Hi everyone, and welcome to another video. So I'm Michael, and I'll be explaining problem number 2 on the Washington Gold HMMT PUMaC team selection test. So in this problem, Brandon draws a magic triangle with vertices -1, -1, 0, 2, and 3, 0. Daniel draws another magic triangle by dilating Brandon's triangle with a scale factor of 100 centered at the origin. How many lattice points are strictly inside Daniel's triangle, but not strictly inside Brandon's? Alright, so this problem can be a lot to take in without a diagram. So I've had Desmos, our handy friend Desmos, draw a diagram of Brandon's magic triangle for us. And I'm not going to draw Daniel's triangle for obvious reasons because that would just be a huge triangle, but we can at least visualize Brandon's triangle. Now this problem is very interesting in that it makes use of a really nice theorem, and this theorem is called Pick's theorem. And to my knowledge, this problem is actually extremely difficult without Pick's theorem, so I'm just going to state Pick's theorem up front and show you how to solve this problem using Pick's theorem. So Pick's theorem says that for every polygon in the coordinate plane with lattice points as vertices, so lattice points are just points with both where both coordinates are integers in the coordinate plane. So for every polygon with lattice points as vertices, the area of the polygon, which I'm going to say A, equals I plus B over 2 minus 1. And what this means is that I is the number of points in the interior of the polygon. So in the context of the problem, I would be, say, the number of lattice points that are strictly inside Daniel's triangle. B is the number of lattice points on the boundaries of the triangle, counting the endpoints. I keep saying triangle, I mean polygon. This holds for any polygon whose coordinates are lattice points. So B is the number of lattice points whose boundary, who are on the boundary of one of the sides of the polygon. And we just have the -1 there added on. And A is just, again, the area of the polygon. So this is really useful because it helps us solve the problem. So let's see how this does that. So we're going to count the number of lattice points that are strictly inside Daniel's triangle, but not strictly inside Brandon's, by counting the number of lattice points that are strictly inside Daniel's triangle. So our final count is going to be equal to number of lattice points inside, I'm just going to call it the big triangle. The big triangle minus the number of lattice points inside the small triangle. So actually we can just count the number of lattice points inside the small triangle right now. So this is just going to be, if we draw the sides of our triangles in, this is just going to be 1, 2, 3, 4, and 5. I know it looks like this point 2, 1 here looks like it passes through a side, but that's actually just a drawing error. So let me just draw that side again. You can see that it actually passes slightly under 2, 1. So there are 5 points that are strictly inside the interior of Brandon's triangle. So this is just going to equal, our final answer is going to equal the number of lattice points inside the big triangle minus 5. And I said we were going to use Pick's theorem here, but up until now, we haven't used Pick's theorem. So we're going to use it now. So how are we going to do this? To count the number of lattice points inside the big triangle, we need to know the area of the big triangle, and we need to know the number of points on the boundary of the big triangle. So let's compute the area first. Okay, let's compute the area first. And to compute the area, let's think about how the big triangle is actually defined. So the big triangle is defined by dilating the small triangle with the scale factor of 100 that's centered at the origin. So that means the area of the big triangle is going to equal 100 squared times the area of the small triangle. So to find the area of the big triangle, what we need to do is we need to find the area of the small triangle first, and then just multiply by 10,000. Okay, so what's the area of the small triangle? To find the area of the small triangle, we're going to use what's called the shoelace formula, which is a formula involving a formula calculating rather the area of a polygon given its vertices in the Cartesian coordinate system. So here's how it goes. So the triangle is formed by these 3 points: 1, 1, 0, 2, and 3, 0. Negative 1, negative 1, sorry. So negative 1, negative 1, 0, 2, 3, 0. We're going to write it like this. We're going to add another copy of negative 1, negative 1 at the bottom. And if you've never seen this before, here's how the shoelace formula works. You add negative 1 times 2 plus 0, 0, 0 times 0 plus 3 times negative 1. Negative 1 times 2 plus 0 times 0 plus 3 times negative 1. Subtract 0 times negative 1, subtract 3 times 2, and subtract 0 times negative 1. This is why it's called the shoelace formula, because it makes that crisscross pattern. Oops. Okay. So what is this number? Let's calculate it. So this is negative 2 minus 3 minus 6. So this is equal to negative 11. So now what we do to complete the calculation, we take the absolute value of this area, of this number, and we divide by 2. And that's the area of our triangle. So this is the area of a small triangle. This is the area of the small triangle. And to compute the area of the big triangle, remember what we're going to do is we're going to multiply the area of the small triangle by 10,000. Of the big triangle equals the area of small triangle times 10,000. So this is just going to equal 11 halves times 10,000. And when we do the calculation, the area of the big triangle is equal to 55,000. That is a very large area. All right, cool. So now we've got the area. So all that remains is to find the number of points on the boundaries of the number of lattice points, rather, on each of the sides of the 3 triangle. And these sides actually do count, and the number of boundary points do count the vertices themselves. So we just have to remember that. All right. So at first, calculating this boundary point condition is really scary because we could just like explicitly compute the equations of the lines. But that seems really nasty. And even if we did, we might have messed up arithmetic somewhere or something, and it might not be a safe bet. So what we're going to do is we're going to think about what the transformation, this dilation with a scale factor of 100 centered at the origin, really means. So to see what I'm talking about, let's switch to a different color and just consider this side. Just consider this side. So in Brandon's small magic triangle, this side only contains 2 lattice points, right? Because it just contains the 2 vertices. But, how do we calculate the number of lattice points when this is dilated by a factor of 100? Well, after the transformation, this blue segment is going to be dilated into something that looks just like it, except with 100 copies of the blue segment. So if you consider what the triangle side looks like at the end, we will have this huge long blue segment, which is made of 100 small copies of the blue segment here. So this would be the blue segment, this would be the blue segment, this would be the blue segment. When I say the blue segment, I just mean the vector connecting these 2 points. And on and on and on until there's 100 of these blue segments just stacked together. And each of these blue segments will have no lattice points in the interior of the segment itself, but will have 2 lattice points as its endpoint. And if we have the entire segment, right, if we have the entire 100 blue segments, there's just going to be 101. There's just going to be 101 lattice points on the dilated version of this blue segment. Great. So now that we have 101 lattice points on the blue segment here, we can do similar logic for the other segments. So there's going to be 101 lattice points on the dilated version of the red segment here, and 101 lattice points on the dilated version of the green segment. So what does this tell us? That tells us throughout all the segments, there's going to be a total of 303 lattice points across all the segments. But we're not done yet, because remember, in our original calculation for how many lattice points were on the blue segment, we counted the endpoints. We counted these vertices. So what we're going to have to do is we're going to have to subtract the vertices, because while we count the vertices in the end result of Pick's theorem, we counted these vertices once in the calculation for the blue segment, once in the calculation for the red segment, and once in the calculation for the green segment, which means that all in all, each vertex was counted 2 times instead of 1 time as a number of lattice points. So in this number 303, we have to subtract 3 lattice points, because those are the ones that correspond to the overcounting of the vertices in the triangle. We don't want that. So in the end, we have 300 lattice points on the boundary of the triangle. All right, so we know the area of the triangle. We know the boundary. We know the number of points on the boundary of the triangle. So now all that's left to do is the calculation. So let's set this up. We know that the area, which if you remember from before, is 55,000, this number here. We know that this area is going to equal the number of points in the interior plus half of the number of points on the boundary minus 1. So we have 55,000 equals I plus 300 over 2 minus 1. 300 over 2 equals 150. So I is going to equal, I plus 149 rather, is going to equal 55,000. Great. So after we do the subtraction, we can see that I is going to equal 54,851. But wait, our final answer is not the number of points inside the big triangle. If we remember here, it's actually this number subtracted by 5, because we want to count the number of points not strictly inside Brandon's triangle. So we have to subtract 5 from our answer. So our final answer is going to be I minus 5. It's going to be 54,846. And we're done.